Okay, so welcome back to part 3 of section 17.2. We're taking partial derivatives. Here we have another example. There's a bunch of words on it, but we can go ahead and see what it's looking at here. Let's see. The problem reads, the average energy expended for an animal to walk or run 1 kilometer can be estimated by the function, that thing, f of m comma v, where the energy used, m is the mass, and v is the speed. Okay, so my inputs are how big it is in terms of how much it weighs in mass, and the speed at which it's moving at, and then the output is how much energy it takes to move a kilometer. Okay, all right. I think I got an understanding of this. All right, so part A, find f of 310. Let's see, f of 310 means go find the function whose name is f and plug in the values 310. I can do that. So f of 310 is going to be 25.92 times 300 to the 0.68 plus 3.62 times 300 to the 0.75 divided by v, 10. That looks like a calculator problem, so let's bring up our calculator. Oops, no, I don't want that. I want that. It's giving me trouble here. One more time, there we go. And then I will make this a lot narrower. And that way I can see them both at the same time. Perfect, okay. So 25.92 times 300 raised to the 0.68 plus the fraction 3.62 times 300 raised to the 0.75 divided by 10. And so that's 1,279. I'm just going to round it to one decimal place, 0.5. And then this is kcal per hour, kilocalories per hour. So a 300 gram object, animal, moving at 10 kilometers per hour would burn 1,279.5 kilocalories to go 1 kilometer. Okay, that's not too bad. All right, so now let's take a look at part B. What does part B ask us to do? Well, the numbers are the same, but it says find the first partial with respect to m and then evaluate. So I need to take a partial derivative. Okay, all right, so f sub m. Let's see, the first term of my function has no v in it, so it's just going to be kind of like taking a derivative. So that's going to be 25.92 times 0.68 times m to the negative, let's see, 1 minus 0.68, 0.68 negative 0.32. I'm sorry, 0.68 minus 1, so negative 0.32. Did that backwards. Plus, okay, here's where things are going to get tricky. I'm taking the partial derivative of this fraction with respect to m. So scratch work over here off to the side. Since v is a constant with respect to m, what that really is it's really 3.62 over v times m to the 0.75. And I'm just going to treat that like a coefficient when I take that derivative. Okay? So that's what I'm going to do. That's how I'm going to treat that thing. And so that's going to give me 3.62 over v times 0.75 m to the negative 0.25. So there's my first partial with respect to m. And now they want me to evaluate it for 310. Now I know at least one person is sitting out there watching this going, is he going to clean that up? Because you could multiply those together. And I'm going to answer with no, because I'm lazy. And my job isn't to find the derivative and clean it up and give the derivative back. My job is to find the derivative and then plug in these numbers. I could plug in a 300 here, a 10 there, and a 300 there, like it sits, no problem, and just put it all in the calculator. So I don't see any reason to clean this up before I evaluate it. So I'm just going to go ahead and evaluate it. So f sub m of 310 is going to be, let's see, 25.92 times 0.68 times 300 raised to the negative 0.32 plus 3.62 divided by 10, v is 10, times 0.75 times 300 raised to the negative 0.25. And I get 2.9. Okay, now here comes the tricky part. Interpret. Well, since I took a partial derivative with respect to m, it's going to be m that is changing. Okay, so I'm going to take a side trip here and go back to derivatives. So suppose that way back when you had y equals f of x, and that x down here was hours, and this over here was miles, and you took a derivative y prime would be miles per hour, because the derivative is always the dependent variable divided by the independent variable units. Right? Same thing with partials, it's the dependent units divided by the variable that's changing units. So this is going to be kcal per hour per, and since m is what's changing, per gram. So what does that mean? Well, I'm just going to take a look at what this is simply saying right here, is that the kilocalories per hour is going up because that's positive at 2.9 kilocalories per hour. So it's increasing for every gram of increase. So if my animal increases its mass by a gram, it'll need 2.9 more kilocalories per hour to maintain that, or to cover that distance of 1 kilometer at a fixed speed of 10 kilometers per hour. So what this is leading us to is, what exactly are we doing here by taking these partial derivatives? Okay. So partial derivatives are defining a rate of change of a function. It's just slightly more complicated than a plain old tangent line because there's more variables. Essentially, partial derivatives give the rate of change of the function, but only allow one variable to change at a time. Since the other non-changing variable is a constant, we just say whatever that other one is, it doesn't change. So f sub m that we just got done doing said mass changes, velocity is constant, or we could think of that meaning it is fixed. But if we had done f sub v, then it would be velocity changes and mass is fixed. Okay? Similarly, if you have more variables, then what you're doing is you're finding one of them changing and the rest of them fixed. Now, if you like to think of things in terms of geometry, like if you thought of derivatives in terms of a tangent line, then what's happening here is the partial derivatives are making a plane that is tangent at a point, and the partial derivatives then tell you the slope of the plane in each direction. Right? But really what they're doing is that they're defining a rate of change. A rate of change, though, can only occur when one variable is allowed to change and the rest are held constant. All right. Suppose that the production for a company is modeled by the function p of x is equal to 250 times the root of x squared plus y squared, where X represents units of labor and Y represents units of capital. Find the following when 6 units of labor and 8 units of capital are used. Okay. What is the marginal productivity of labor? Well, I remember from my 212 that whenever I saw the word marginal, that meant I was taking a derivative. And in 212, that was easier because there was only one variable. But now I got to figure out what that means. Well, the marginal productivity of labor says change labor, fix capital. Or, for us, find P sub X. And so what this really tells me to do is says find P sub X for 6, 8. And now that I've reduced it down to this problem, I know exactly what to do. Take a partial derivative, chuck in a 6 and an 8, call it a day. All right, so let's go ahead and do that. All right, so let's see, what do I do here? Let's see, I got to take a partial derivative first. So P sub X. Well, the 250 is a coefficient, so it's going to drag along. And then I've got the root of a function. So that's going to be 1/2 times the quantity x squared plus y squared to the negative 1/2 times the partial derivative of the radicand with respect to x, which will be 2x. Okay, now if you're wondering what I just did there, I'm making use of this rule. See, the rule for derivative said the derivative of the square root of x, that's the derivative with respect to x of x to the 1/2. That's going to be 1/2 x to the negative 1/2. But if it was the derivative with respect to x of the root of a function u, that's just the derivative with respect to x of u to the 1/2. So that's 1/2 u to the negative 1/2 times u prime. And then when we take and find our u prime, what we're really finding is a partial derivative because we're doing partial derivatives here. So that's the rule I'm using here. So given that that's my rule, let's go back and take a look at where the pieces came from. So the 250 is just the 250. There's the 1/2, that's the u. There's the u prime, the partial derivative here. The 1/2 and the negative 1/2 are kind of from the formula if you want to think about it that way. Okay. Now at this point, it's just a matter of plugging in a 6 and 8 and call it a day. So P sub X of 6, 8. Let's see, that's going to be 250 times 6 squared plus 8 squared to the negative 1/2 times 6. Now if you're wondering where the 1/2 and the 2 went, they multiplied together and became a 1. 6 times 250, well, 6 quarters is $1.50, so it's 1500 times 6 squared plus 8 squared to the negative 1/2. I'm going to grab my calculator again. Let's see, 1500 times the quantity 36 plus 64, end of quantity raised to the negative 0.5. I get 150. Is that 150 or negative 150? 150? So what does that mean? Well, marginal says change labor, fix capital. So productivity will increase, because that's a positive, by 150, whatever these units of productivity are, per unit of labor increase. So productivity will go up productivity will increase by 150 units if labor increases by 1 unit. 6 to 7 because labor was fixed at 6. Right? And we fix capital at 8. Okay. Same logic. What's happening over here? Well, this is going to be the marginal productivity of capital, so that just means do it the other way. Change capital with fixed labor. So P sub y of 6/8 is ultimately what we're going to calculate over here. All right. First step will be to find P sub y. So P sub y of xy, 250 times 1/2 times x squared plus y squared to the negative 1/2 times 2y. P sub y of 6/8 then is going to be 250 times 6 squared plus 8 squared to the negative 1/2 times 8. Let's see, 8 times 250, so 8/4 is $2. So 2,000 times 6 squared plus 8 squared to the negative 1/2. 6 squared is 36, 8 squared is 64, 36 and 64 is 100, 100 rooted is 10, 10 downstairs is 1/10, so that's 200. Or put it in your calculator if you don't trust me. So P sub y of 6/8 is 200. So now what's going to happen? Well, productivity will increase. How do I know it's increasing? Positive number. So it'll go up by 200 units, whatever those units are, if capital increases by 1. Unit from, what is that going to be? From 8 to 9, right? Labor stays fixed at 6. So that's what we're looking at here. We're looking at what is happening. Partial derivatives tell you the change, but we can only change one variable at a time. Now, technically, that's a lie, because there are techniques for allowing both variables to change, but they are outside the scope of what we do in here. You may run into those later in your math career, but for right now, we're saying only allow x to change or only allow y to change. If you want to change them both, that's a much more complicated problem. Okay, we'll save that for later. We're at almost 18 minutes here, so we'll come back and start second order partial derivatives in our next video.